In this video, we will play around with version 2 attempt at rotating canards, an on-board adjustment system, a few other fin variations, plus some better ways to compare all these fins more scientifically. After the release of the previous video, a few have sent in photos of earlier canards. It seems all of these are fixed canards, or a variation on the same concept. Decrepit was adamant that rotating canards were much better than fixed canards for improving performance, so I focused on these. I redesigned the modular canard system to load the camera from the top of the board, and also to bring the canard angle stop adjustment out to the top of the board for easy change on the water. Thanks again for Decrepit for the help with cutting the board and fixing the new system in place. I filled the air prism with salt water via a tiny hole, then plugged the hole with silicone. It appeared nearly impossible to remove the last air bubble, so left as is. I pinned the model boat rudder shaft collar to the horn as well as to the shaft. To be sure that the canard wouldn't rotate past the adjustable stops, I also pinned the steel rudder to the shaft, then siliconed the 3D printed canard to the rudder. The cam adjustment bolts are connected to flexible rubber tube, so it can make the 90-degree bend and be adjusted at the surface of the board. The soft rubber is also to cover the case where I accidentally step on them. The canard is loaded into the board from the bottom, held in place by the main fin, then the action camera is loaded in from the top. The camera is held in place by a cam lock mechanism, which in turn has a safety cover bolted on.
Yeah, same fucking thing.
Not the same, man. This is new tech.
New tech.
Well, it's not. No, it's not. This is.
He's got the camera and everything going.
The action camera can be turned on and off by pushing the buttons with a screwdriver, and its indicator light can just be seen to see whether it's working. Countdown. On the first run, I set the cam to allow the canard roughly mid-rotation. Unlike previous attempt, the canard rotated the correct way. The weed plough holds a few air bubbles initially, but they are soon knocked off. Everything felt fine, and there appeared to be no drag, and I could point into the wind well. After a few runs, I stopped to adjust the canard stops. However, it turns out very cold fingers can't grip slippery rubber very well, so I gave up with any adjustment. The canard did not collect any of the thick Albany weed. The action camera also survived and recorded the whole session. Since the tide was rapidly rising and the wind forecast was it would turn ballistic in a few hours, I came in to change to version 2 of the foresail canard fin. In hindsight, I should have just removed the canard and gone with the plain fin, but I had a bunch of fins to test and actually forgot this combo. This foresail canard was a slightly improved version from V1 with longevity improvements, but essentially the same. This fin also performed well as expected, and peak speed of the day was reached with this fin, but this was most likely because this run had the best tide and wind combination. It's probably worth mentioning that for all these tests I kept the same sail setup, harness line position, mast base position, etc., and the same type of runs. I did about 10 kilometers on each fin to get a reasonable amount of data. Whilst I didn't feel any drag at the time, when I stopped, there was a massive amount of weed collection, so this design in its current form is not suited to weedy areas. Next fin up was the chevron trailing edge fin. This was inspired from the chevrons used on jet engines to reduce noise from turbulence. I also added a small amount of cotton flock to the epoxy in this fin, thinking it would stiffen the fin. However, it turns out this made it slightly more flexible. This is a deflection test where I load the fin 18 centimeters from the board with a 20 kilogram bag of salt. Each fin has exactly the same amount of carbon rod stiffeners. On the water, it definitely didn't feel like it could head upwind very well compared to the two previous fins, but otherwise performed fine. The next fin I decided to run was the rotating canard again, but this time with the canard fully locked. There is still some slop in the canard, but the rotation angle was much smaller than the initial run. Unfortunately, this meant I could not install the main fin, so I started adjusting the mech to allow the main fin to be installed. Whilst doing this, I managed to drop the board and the trailing edge of the canard broke. It appeared there was still more area behind the rotation point than in front, so I decided to continue with this setup. I figured the action camera would record whether the rotation was correct or not. Unfortunately, but unknown to me at the time, the action camera failed shortly after I switched it on, so there was no footage to determine if it did indeed rotate correctly. Slightly to my surprise, this combo worked well like the previous canards, and I could head upwind well. I managed the same peak speed as the foresail canard. The next fin I tested was a fin I called the Eagle, as it has a trailing edge with feathers inspired by the eagle. A previous magpie version wasn't tested, as I managed to rip all the feathered trailing edge by some severe dredging. The epoxy in this fin was loaded with as much milled glass and cotton flock as I could extrude with a loading syringe. Again, the result was opposite what I expected, and this fin was so flexible the 20 kilogram test load kept slipping off, so I had to reduce the load distance from the board. You can still see it deflects quite a lot compared to the green fin used with the rotating canard. Because the general consensus is flex in a fin is not desirable, I thought this fin would perform worse than the stiffer purple chevron fin. However, it performed much better. Since the wind and chop had also increased, it felt rock solid or more stable. Because of this, I used this fin for the remainder of the day with much smaller speed gear when the wind booted. A quick look at the data that evening showed the Eagle fin did indeed perform well, as did the broken canard, so the next day decided to try the broken rotating canard with the Eagle Flexy fin. There was much less wind, but I tried as best as I could to rig everything the same as the previous day. Again, all seemed to work well. I hit something near the end of the session, but I dared not step off the board till the end of the session. When I finished, I noticed all the feathers had been ripped off.
What are you doing?
I suspect I hit one of these razor clams. Now, how to compare all these fins instead of the touchy-feely subjective on-water experience. The first is to compare the tracks from the GPS. The wind was coming from the northeast, and for each session I went upwind for each tack to get as far upwind for a bear away or speed run in the flattest section of water. You can probably see just from the tracks that the central chevron fin struggles to get upwind as well as the other fins. The three canards look roughly the same, and the eagle fin between the chevron and the canard fins. Another way to look at the data is with polar plots. These show the differences in various fins, but they are not that clear to tell definitively what is going on. A sailor who calls himself Board Surfer suggested another way to look at the data by graphing the percentage of time sailed below a certain angle of wind versus the sailed angle of wind. It sounds weird, so to put it another way, the x coordinate is the absolute angle to the wind, and the y coordinate is percentage of points in this data set that is less than this angle. The linear section of the lines is the most interesting part. Here you can clearly see the difference in fins. The further to the left the curve is, the better. The canards clearly are able to head upwind better. However, this graph gives no indication of speed, and it's more important to be able to go upwind fast. So I graphed the average VMG, or velocity made good, for all the angles I sailed to the wind. Velocity made good is the component of my velocity that is directly into the wind. The faster the VMG, the sooner you can get upwind to do more bearaways, or is a significant advantage in race conditions. This shows that at lower angles to the wind, all the fins behave roughly the same. However, the canard fins perform significantly better in terms of VMG. I also graphed the average velocity, or my speed in the water, versus the angle sailed to the wind, and here it gets even more interesting. For lower angles into the wind, the fins all travel at roughly the same speed, with just a slight drag penalty for the canards. However, the rotating canard seems to accelerate at high angles of attack. On the way home I did a brief test with the board and broken canard on my roof rack to see if the canard follows the airflow or flips. Since it stayed with the airflow, it appeared the canard performed as expected and rotated the correct way. So far I haven't determined whether rotating canards are superior to fixed canards, but they certainly seem to improve performance of the fin quite significantly. It is thus strange why they have mainly died out. On the flip side, no birds or fish use canards, so they have evolved a potentially better way of achieving the same thing. During my research into bird wings, I stumbled across an old paper that claims a 35% reduction in drag for a wing that is only just being rediscovered. The better than expected performance of the yellow flex fin is a small step in that direction. This is quite difficult to implement unless you use 3D printing. So in addition to further canard variations, stand by for more nerdy fins to come. Thank you.